Hello, everyone. You are welcome to the topic 4. We are still in topic 4, but now we are in clip 2, where we discuss more about as introductory part for the fundamentals of artificial intelligence. In the previous clip, we discussed or we introduced what we mean by artificial intelligence, and also we introduced the intelligent agent, and we said that the intelligent agent is the engine where we use to solve or to achieve some tasks, and those tasks that we need to formulate, or some problems that we need to formulate. And we also discussed a little bit about what we mean by problem formulation in the previous clip, and today we are going to talk in more detail about problem formulation and steps how to solve these problems. Okay, so in the problem formulation, actually we can say that one of the best way to handle many problems is by using state transition graph or tree. So this gives us very good formulation of the problem, and also we can handle such kind of problems relatively easy. And however, of course, not solving the problem is always easy, as we will see later. We have here 4 significant parts to formulate any problem. That we need, of course, initial state, as any problem that we have initial condition to solve, or we need to start from somewhere. So because of that, we need to define our initial state, or the initial states can be given actually. Then we have the operator set. What we mean by operator set? The intelligent agent, when they are in any state, they have some legal operations that they can use from that state. The operation is not necessary to be the same for each state, or so we need at each state we have some set of legal operations, or we can call it later when we talk about multi-agents, about strategies. But here let us talk about operators. So we need to move from one state to another state, so we have some legal operations that we can do. So when we make this operation, then we move from state 1 to another state. Okay, and then we have the path cost. What is the path cost? The path cost is anything, you can see that it is anything that we need when we solve the problem to reduce or to minimize, or at least if we cannot reduce them, so we know that this path cost is something not like preferred. So the path cost, you can see it about, for example, time to move from state to state. It can be seen as money to pay from state, to move from state to state. It can be seen as, for example, maybe risk factor increased if you go from that state to that state. It can be seen also like maybe violation of some rules to go from this state to the other state. So anything that you can think about to move from state to state as a cost, or as something that we like to avoid or to minimize or to reduce, this can be seen as a cost associated with that state. So not all costs are the same, or not the cost from moving from state to any state from other state is the same. So they can be different from state to state. Okay, and finally is the goal test. So of course we are in the intelligent agent, they need to achieve some goal, as we mentioned before about this vacuum cleaner, that they need to clean the room, for example. So the goal is to clean all the room, for example. So we have goal test. Sometimes we have one goal, and sometimes we have multiple goals or many goals in the problem. Not necessarily that all goals are the same. So some goals can be better than others. So in that sense, finding the optimal goal can be also a problem. Some problems it can be easy to find the global goal, So it is optimum solution. Some problems it is very difficult to find the optimal solution, so we can be satisfied with some solution which is okay for us. It is not the optimal one, but it is okay. What is the how to measure the optimality? What is the how to say this goal is better than that goal? Actually, one thing that we can achieve this is by using the minimum path cost. For example, the solution which can achieve the goal with the minimum path cost, of course, this can be one optimality measure, okay? Or it can be the goal value. So some goals, they have very big value, some goals, they have less value. So it can be also like some joint measure for the costs and the goal value. It can be also, so it can be measured as the optimality of the obtained goal. Okay. Then how to achieve or how to solve the problem? First, when we reach to any state, then we need to check if it renders a solution. So actually, some the problem formulation and the searching algorithm or the procedure to solve the problem. So we need to answer a question: is there a solution or goals at all or not? You know, some problems based on the initial state, as we will see also later, that they might not lead to any solution. So in that case, you just lose your time searching for something does not exist. Okay. Then once we answer this, so this solution, this problem, then is it good solution? So as I said, that it is based on low path cost or the value of the solution is good. Then what is the cost associated with time and memory required to find a solution? So actually, be careful that this is different than it can be different than the path cost that we mentioned before, because the path cost can be, for example, the time required for the car from going from state to state, or it can be the cost, not time, it can be the fuel consumed, and it can be money, it can be anything. But to solve the problem on computer, there is also time and memory required to solve the problem. So there is another kind of cost. Of course, you can put both of them in the problem formulation, but keep in mind that it can be different. So the cost associated to solve the problem, it can take very long time. For example, to find the optimal solution for some problems, and you find that using such kind of searching technique, you might need, like, for example, 2 years of your computer running to find some solution. So this, of course, can be very costly. So you need to find some other way to solve the problem. Not this using this searching technique. Maybe you can start to think about other searching technique which can reduce the time and the memory required to solve the problem. I give you just one simple example. It is already there in the slides. When you read the slides, you can find them. So, for example, the chess game actually, it has the number of movements. For example, if you have this chess game, okay, where we have 64 square here. So now when you say that if you play against another opponent, A against B, so if you move one item from this square to this square, for example, of course, how many options that you have in the beginning, in the initial state. So this is the initial state that you have all your items here on the board, okay, and also your opponent. So now how many possibilities that you can start? So you have many of them. Maybe you have 8, maybe you have 10 in the beginning. So from the initial state, you might have 10 states, and based on what you have, what you move, also your opponent, they have in the beginning 10 movements possible. So over each one, you have also 10 responses, and from this response from the opponent, then you might have also more than 10, and so on. If you want to expand the chess game in this way, in such a tree, do you know how many states you need? You will need 10 of the power 64. Yes, about 64 states. This means one, and in front of it, sorry, not 64, 46. 10 of the power 46, which means that it is 1, and in front of them they will have 46 0. Do you know what this means? It means that more than the number of atoms on Earth. You know, the number of atoms on Earth is less than this number, or maybe close to this number. So it is really, really huge. There is no memory that I mean, manufactured memory, they can handle all this size. Okay, so it is almost impossible, or it is actually impossible with our current technology to make the whole number of states only in one chess game, which is also, remember, in this chess game we didn't consider any uncertainty, so it is certain problem. It is a certain, so we don't have uncertainties here. We are not dealing with a practical or real situation problem, so we deal with well-defined environment. This environment is well defined, and also we assume that we have full information, so everything is clearly given. Okay, so even in that case, it is not that easy to represent them as a tree. Okay, so you need a huge memory and you need a huge time to solve this problem. Maybe if you want to compute the exact way how to move from the initial state to the goal state. Of course, the goal state is that A win. So if they want to go in the details from the initial to the goal, okay, in considering all possible ways the opponent will play, maybe they need hundreds of years of computation over a supercomputer. So you can see that it is not possible. So based on that, we have many other like heuristic techniques to solve such problems, as we will discuss also today. Okay. Of course, Toy's example is very nice to start with, so it can give us some like impression how things are going, and I am going to explain it through some like games. So to explain what I mean by state and nodes. Actually, there's difference between state and node. Let me, for example, this is one easy and nice game that we can use to explain things. So this is called 8 puzzle, where you might have numbers like that, and this is, you have one blank square, and you start move this blank until you reach some goal or target state. So this is called state. Okay, and now let me go to the to some blank screen. Yeah, so I can explain a little bit more. I will have the whole screen here, as you can see. Now let us start that we have a state. This is the initial state. Assume that this is the initial state that we want to reach with, or to start with actually. And then we have blank here, and then we might have like 3, 1, 7, and we have here 2, we have here maybe 4, and here 5, and 6, and 8. Okay, so now we have this state, and now we want to reach to our goal, and our goal or target state, it can be in this way: 1, 2, 3, 4, 5, 6, 7, 8. So this is the target, this is the goal now, target, and this is the initial state. This is the initial state. Okay. Now this is a state and this is a state. So this is the initial state and the target state. But as a data structure, we can talk about nodes. So what is node now? The node contains the state itself, but also the operations that associated with the state. So if you start with this state, how many operations that you can do? You can take this blank. If you look to this blank, okay, this blank state B, okay, we can take this B either up. When you take it up, it means that you take the 3 down, yeah? So you can take the up, the operations associated here is up, down, and also to the right. So actually we have 3 operations that we can do with this state. Okay, then we will move to 3 nodes or 3 states. Of course, when we talk about node, remember this. When you talk about node, you talk about data structure. So in the node, you put the state itself, the operations that you can do over this state, and the cost associated with the state, and also the parent of the state, because now this will be the parent of the next states. Here we will have 3 different states, as you can see. Okay, now if you go up, you will have here what? Okay, now I go up, then the blank will be up. Here we have 3, and here everything will be the same. So it will be 8 to 8, 4, 5, 6, as you can see. And if you go to down, then we will have the other state. It will be, if we go down, then 4 will be up, and 3, 1, 7, 2, 8, 5, 6. And then if we go right, to the right, then we will have, sorry taking this long time, but I want to explain, because those are concepts. So I'm trying to explain that concept so you understand what we mean later. So here we have the right direction. If we go to the right direction, then we will have 3, 1, 7, and here will be 2, and in the beginning, in the middle, we will have the blank, and here is 8, 4, 5, 6. Now we have 3 states, and in each state we can define a node. So here is, if it is node, then we will have also inside this node as a data structure, the state itself. We can call it, if this is a state 0, then this can be state 0, 1, for example, and we have the operator. What are operators associated with this node now? If you think a little bit, you can find that from this you can go to either to down direction, to down, or you can go to the right only. So actually you have 2 operations that you can do here. So you have down and right, okay? And the parent state is 0, and the children state that you can go from this, that you can also define them here. So now in the down, if we go to down, then we what are the operations that you can do for this state? Okay, we can go up, and we can go also to the right. So we have up and right state. From this state, actually this state, the only state in this toy or a game, on this game, that it has 4 possible, or the maximum number of branching or of movement. So we can go either up, or down, or right, or left. So here we can go to 4. Okay, and from this one, it means that we can go up to 4 other states. Okay, from this one we can go to 2 states. Okay, and from this one we can go also to 2 states. Okay, but it is important to remember, now if from here, now we are here, if we go to take the because okay, this is the blank, and from the blank actually we can go down. If you go down now, what happened? If you go down, actually if you go down, you will come again to the initial state. So this should be taken into account. So we try to avoid such kind of like repeating states. Okay, because now if you go down, if you take this blank down, the 3 will go up, and what happened? We will come again to the initial state. So if we use up to reach here, using down, we come back. Okay, and also here with down, we got this state. If we use this operation up, then we will go another time to the initial state, and the same will be for this problem. So actually the available, not 4 is the totally, like theoretically you have 4 movements, but remember that if here you go right to get this one, if you go left, one of these children states will be the initial state again. And if you stuck here, so you will find yourself just you repeating yourself. So the game can be easily. This is actually the tricky in these searching techniques. So we always try to avoid such kind of repetition. So if you go through some like well defined game like this one, and then you can stuck in one point, because if in any of these children that we are going on that we have them before, it means that you are repeating, not necessarily of course from the beginning, but I just wanted to explain to you one example. But this can happen in any stage in this game. Maybe after 20-30 stage you will have some stage in the middle. So what it means that you are repeating. And this one is one of the interesting problems in computer science. They try to handle and to take into account, and actually to solve this problem, or to handle this problem. This is why we need to memorize or to keep in memory all states that we generate. So because every initial state we try to like compare it, that if we had it before we have to kill it. So we don't come again, otherwise we will have like infinity loop in the game and you will not reach to anywhere. Of course, there are many different techniques to handle this, like for example, insisting or inserting some probabilistic movement with the states in big and difficult problems, to try to get rid from this stuck, because you're stuck in any point. So we can, if the problem is very complicated and it has like billions of states, that it is very hard to memorize everything. So one way that maybe approaching the global optimum solution is by reducing some uncertainty somewhere. So, but there are different topics here, so we try to not to go to that level. Okay, we just give some general description about the problem and how to handle it. Okay. Yes, you can find what is next is almost the same what I explained now. So you can see another problem. It is called traveling salesman or salesperson problem. TSP, it is well known in computer science that you start from it is emulation, that there is a salesperson that he or she wants to sell stuff, and the idea is to start from certain city A to the end city L, and those cities are well connected to each other, and to move from each state or from each city to the other city, we have some cost. The cost can be like time required, or it can be the distance d. Okay, and the idea is not allowed to go through the same city twice. So if you go from A to B, it is not allowed to go through B again. So it is not allowed, for example, from C to go to B before you go to J. So for every city that you can pass it only once. And the idea is how to find the minimum cost. And the cost here we mean the either the minimum time to cover all cities, or for example to minimum distance. So you start from A, reach to up to L, and then going back to A again. So this is one of the NP problems, and it has many applications in computer science, and also in manufacturing of very high scale or very large scale integrated circuits, and they have many different applications. So how to solve the problem, or how to handle these problems? Actually, now we show one way. Remember, this is only one way to formulate certain class of problems, because we are going in this course to talk about machine learning, and how is the machine learning, how to give some inference to some problems. We can talk also about some probabilistic models, and we can talk about different ways of handling or representing artificial intelligence. But now we are talking about problems, certain kind or certain class of problems that can be represented as a tree, or as like a graph, and then we want to implement searching technique to find the solution over that graph. So this is only certain class of AI. I might say that even there is a debate if these searching techniques could be considered as AI or not, but anyhow, they say that to say that it is AI, then it should be also associated with some intelligent way of extracting information from available data, for example, and how to deal with uncertainties and so on. But let us take it as an AI and talk about this. So the searching algorithm actually is just optimization techniques. So it is optimization techniques to solve for integral problems. Okay. So the idea is how to generate the states, as we show in the puzzle 8 problem. Generate states, and based on these states, we expand. It can be expanded, and also we test each state if it is the goal state or not. This is simply what we are going to do. So searching is the tricky part here. How to search for the solution? We have different kind of searching algorithms. They are well known that it can be deterministic algorithm, or it can be heuristic algorithm, as we will see, or it can be also probabilistic searching techniques. And we will not going to go in very details about searching techniques. It is a big subject in computer science, but we are just touch it very lightly. Okay, searching for the solution. Okay, now we talked about state and what is state and node. Okay, and you can, of course, it is important, by the way, that you read the slides. They are I am trying only to give the main concept of the topic. So remember that for any expanding process that we are doing in the searching, the node or the state that is waiting for expanding, we can call it that like thing, or for entire that it is waiting. So it is waiting node or waiting like state to be expanded. So and now which one that we should expand, which one it can wait. So this actually depends on the procedure of the searching algorithm. And okay, now let us see how to explore some of the searching algorithms in order to find the solution. And remember that all the time that when you come to certain, you expand, for example, what is the first one that we want to expand? Of course, the initial state. So we start with the initial state, and then based it on the available operators in that state, we can expand them. And once we expand them, then all these new states can be fringes that they are waiting, or frontier. So which one that we select, this is what we are going to explain. Now the searching strategies that we are talking now, we need to evaluate them based on 4 evaluation criteria. First, completeness. What we mean by completeness is it guaranteed to find a solution if there is one? Of course, there are some problems that might be quite difficult, even that we are not sure if there is a solution or not. Okay, by the way, about this puzzle 8 algorithm, or puzzle 8 problem, there are some initial state that you cannot find solution. So actually 50% of them, they might not have solution at all. You cannot reach to the goal. So because you know that for that game, we will have like 9 factorial possible states, but those which you can find solution is only 9 factorial divided by 2. This is for very, very simple like toy, like this puzzle 8 problem. So the completeness is a measure for the searching technique, which can guarantee that it will reach to the solution if there is solution. Okay. Time complexity is how long it takes to find the solution. Space complexity is how much memory is needed to find the solution or to perform the full search until solution or until target. Then the optimality. Optimality means that does the strategy find the highest quality solution when there are several different solutions? One problem is the salesperson problem, traveling salesperson problem that we mentioned now. So optimality means that it will find the minimum path or the minimum distance solution, or it just will find one solution and that's it. So this is also that one criteria. So we have these 4 criteria when we like to apply any searching technique. What kinds of searching techniques that we have? We have mainly 2 kinds. One is uninformed or blind search, and the other one is the informed or heuristic search. What is the uninformed? Uninformed means that you don't have any previous information about the problem, and you just make this expansion of the states or the nodes that you have, and just you are searching where is the solution is. The informed or heuristic search, then you have some knowledge about the problem, and then if you have any knowledge about the problem, how can we use this pre-knowledge in order to minimize the cost or cost of time cost and space cost in order to find the solution. So it can speed up the process if you have any information available about the problem, but of course this information might not complete, because if the information is complete, then it will be very easy to solve the problem. But most of the time that we have just some rough or noisy information or noisy data actually about the problem itself, then we can build some deterministic or probabilistic algorithm in order to speed up the searching process. So this is mainly the two kinds of strategies. Of course, we can also think about this random search, but the random search actually in many times they will end to no way. However, this random search sometimes is used to explore the problem. So we have some problems that we have no idea about it, so we can use just like selecting random operators in each time in order to build some knowledge about the problem itself. Okay. But here we talk about only the uninformed or blind search and informed or heuristic search. The first kind of blind search is called breadth first. Breadth first simply that you just, for example, you start with the initial state, then you look from the initial state all the branches from the first state. So assume here we have only 2 branches. This is the second one. Then you go to the first, you select any of those. Okay, there is no pre-reference here. You select any of those, and then you go to the to branch them, but don't branch further. Go to this state and branch it first. Then you go to this state, branches this state, and so on. So it is called breadth first searching. So the breadth first searching is guaranteed that you can find the optimum solution, and it is complete. But of course, it will require very large time as well as very large space in order to find all possible ways to handle the problem. So if we assume that the average number of branching is x, okay, at each state, this means that from each state we can generate like x states or x nodes, then assuming that they are the same. Of course, in the puzzle 8 it was not the same. Sometimes we have 2, sometimes we have 3, sometimes we have 4, and if we kill the repeating states, then we have 1 or 2 or 3. So we can see, actually we can compute the average number. Depends on how many ones that you have, how many 2s and how many 3s, then you can compute the average number of branching. But here if we assume that they are exactly the same, then the first time we have the initial state is divided into x states, branch it, and each of them will be divided into x. So what we will have x squared. Each of them will be divided into other x. Then we have x to the power 3 until we come to the depth. So if we are reaching to the depth of d, then we will have x of the power d states. This is the breadth first. So now we take simple example. If we assume that we have a problem with an average branching factor of 10, so from each state we can generate 10 different states and compute how many states required to reach to depth 6 and how many states required to reach to depth 20. And now assume that you have a computer, and the computer, it can solve for 1 million nodes per second. So in each second your computer can check the goal state and branching 1 million node per second. This number is quite not very large actually, but it needs good computer. Now with this computer and this requirement, so if we have up to depth 6, so we will have 1 plus 10 plus 10 square plus 10 cube until 10 of the power 6. So because the number is exponentially increasing, so the number is actually close to 10 of the power 6, because the number behind it is 10 of the power 5. 10 of the power 5 is much smaller than 10 of the power 6, is only 1 over 10. So the number is, we can approximate it like 10 of the power 10 of the power 6. And since the computer will solve for 1 million per second, and here we have 1 million, then the computer to reach to depth 6, it will need only 1 second. But the same computer here, if we are looking for depth 20, if we are looking to go to depth 20 in the same toy or the same problem, then we will need 10 of the power 14 seconds, and 10 of the power 14 second is equivalent to 3 million years. So your computer needs 3 million years. I hope that you are alive at that time to check the solution to only to reach to depth 20, not even that very large or very deep depth. So you can see that the breadth first can be nice strategy, but not efficient at all. Even it is a complete a strategy or a complete searching algorithm that it can reach to the optimum solution, but it is not efficient in terms of memory as well as in terms of space or time. Okay, now this is called NP hard. So I hope that now you know what we mean by NP hard, non-polynomial hard or non-polynomial complex problems. It means that the complexity of the problem is increasing very fast with the number of states or the number or the size of the problem. So there is no polynomial. They can cover the time required or the memory required when increase the number. So you can see that 10 of the power 6, it can only 1 second, but 20, oh sorry, 6 is can be solved for 1 second. But if you check 7, it might need 10 seconds, but 8, so the number can be increasing very fast. So it reached only to by 20 depth that we reach to 3 million years, and compare 1 second with 3 million years. Of course, this 3 million years, I just computed them from 10 of the power 14 seconds. I hope that I didn't make mistake in that computation. Okay, and second one is uniform cost. So the uniform cost that for those which are in the frontier nodes, so we select one which has the minimum cost. We select one which has the minimum cost. If we have different costs about to move from state to state, if we have different costs here, like for example, this is the cost 1 and cost 2 and cost 3. Once we solve them, the second one that we expand, not we start from anywhere. We start from the one which has the minimum cost. For example, if C2 is the minimum cost, then the second one that we expand is this one. Okay, and then all the time we are looking for the minimum cost to expand. So it is if actually the cost is as the depth, then it will be the same as the breadth first search. Okay, for the uniform cost, let us take this simple example. So we have this simple example that we are starting from the initial state S, and this is the goal state J. So now we want, this is the cost for each state. Okay, now we start by expanding all these states. So we expand A, B, C. Now, when we expand all of them, which one we continue? Of course, we will select this one, this state, because this state has the minimum. So from S, we go to A, and we start by expanding A. Once we expanding A, we reach to J. So now we have SAJ. What is the total cost here? Is 10. We keep it here. Do we need to expand more? If we look, yes. Here we have 5. Okay, remember now we didn't check for the goal state yet. Okay, so because once we come to A, we check A. If is A goal state, no, then we expand it to 10. Okay, then we have J. Now we don't expand J, so we don't check it yet. So we go back, we check here, we have 5, so we come with 5, and we check B. Is B is a goal state? No, then we expand it, so we have now SBJ with total cost of 10. So here is the total cost is 11, sorry. Yes, so now we have SA and SPJ, and the total cost here is 10. Okay, now we stop here. Now we check, is there anyone less than 11 or 10? No, because the cost here is 15. So we don't expand C. Okay, now which one you select? Of course, you select this path is SBJ. SBJ because it has the minimum cost. We come to J, we make the test. When we make the test, we find this J is the goal. We stop here. If it is not goal, then we start to expand this more. And then we go in this way. This is called the uniform cost. Okay? It can be seen that uniform cost, it can be like much faster than the depth first, the breadth first expansion. The second searching technique, or the third actually, is called depth first. The depth first is simply need much less space than the breadth first, but it needs very long time, especially if the goal is very deep, and actually sometimes it will not reach to any solution. Why? The idea here is that you start from the initial state, you go to 2, you don't go to the other one. No, from 2 we go to 3, and from 3 we don't branch 3. We go from 3 to 4. We don't branch 4. From 4 to 5, and now we reach to end state. Here we cannot move anywhere. Well, why? If you ask why we cannot go anywhere from 5, because for example at this state, you don't have any available operations to move. So the movements here is null. The movement space is null, so you cannot move anywhere. So it is like leaf, or it can be seen like end state. So now it is ended state. What we do? Okay, now we go to 4. We return from 4. We don't go from 1, no. We go from the last parent and we branch it. So we branch it to 6. Now it is 6 now. And that now from 6 we branch it to 7. Of course, at each state before you branch, you check if it is goal or not. Don't forget this operation. Now we come to 7. Is 7 is goal? No. And it is also dead space. So since it is dead state, then we go back. Of course, we don't have anything from 4. Then we have from 3. From 3, we can go to 8. And 8 is dead. Then we go back to 2. Now we go to 9. 9 is dead. Then we go back to 1. From 1, we can go and branch it. So we have here 10. From 10, we can go to 11. 11 can be expanded to 12. 12 is expanded to 13. 13 is dead. Go back to 12. Is there any other branch? No. Go back to 11. Is it possible to expand it? No. Go back to 10. From 10, go to 14. So from 13, we go to 14, 15, 16, and so on. So you can see that how it works. This is called depth first search. Just imagine that if this branching is going to infinity, if there is no solution in this branch, so it will continue forever and you will not reach anywhere. Okay, and sometimes the solution is there, but there is another solution. For example, here, for example, just imagine that this is the goal solution here. Okay, and you don't know, of course, this is the goal solution, so you can go very deep and you can spend a lot of time before you're going back, and then you realize that the goal is here. Okay, so we don't know. This is the depth first. It can be good solution. Actually, it can be good if we have problems with many possible solutions. Okay, if you have problems with many possible solutions, assume the breadth first that we talked before. So the breadth first, we said that to reach depth 20, you will need 3 million years. Okay, of expansion, 3 million years of expansion to reach to depth 20. Assume now that the solution is available at depth 20 here. How much time that you will need to reach here? And we said that each time is 1 microsecond to move from 1 to 1 in that computer that we mentioned in the previous example. Actually, you will need a 20 microsecond only. It is very, very little time to find the solution if the solution is at depth 20, but in this branch. Okay, so it can be much faster than the breadth first technique, but of course nobody knows. Maybe it is at depth 20, but maybe not here, maybe at depth 20 here. And here the computer needs to search, for example, for 100 billion states before it comes back and reach to the solution. Nobody knows. So this is actually, I like you to think about the complexity of such problems. It is not that straightforward. Even the implementation of the computer to write a code to solve these problems is not difficult. Actually, you can write code with 20 lines or using ready packages, or you can write yourself with C code or with Python or with MATLAB. You can write simple code to solve this breadth first or the depth first, or even star algorithm, searching algorithm, whatever the searching that you use, you can simply implement them in computer. But actually, what is not simple is to find the solution. Finding the solution can be quite tricky. This is the reason that we always prefer the informed searching techniques over the uninformed. Of course, sometimes we don't have information, then we have no other chance. But before I complete this part, I would like to mention that there are some also modifications for the depth first. For example, they start to use, for example, the depth, but with specified number of depth. For example, they say we start with depth equal to, for example, with 5. Okay, now it will go until 5. Not going anymore. If they didn't find the solution, go back, and then go to the other branch. Once we check all the 5 and we didn't find any solution, then we can go to depth 6 and we go from the last information that we have to check to depth 6 or depth 10. So we try to join both the depth first and the breadth first together in some algorithm which can be better than depth first and also breadth first alone. There is another way, is called bidirectional. I can maybe find them. This is the uniform course that I mentioned now. I mentioned before, actually, we go to the first section. Depth limited, yes, we have iterative depth, and we have the bidirectional technique. The bidirectional searching technique actually can be quite efficient if we have, or if we know the goal. You might ask, do we know the goal? Yes, in some problems we can also know the goal. For example, this simple problem of puzzle 8. So we know already the goal of the puzzle 8 game, okay? And we have the initial state. So this is the goal. We know the goal before, and we have the initial state. Then from the goal, how to go in bidirectional? Go to bidirectional that in the same time we branch this, and in the same time we branch the goal going back. So in the worst case that we can reach to the between both branches in the middle. Once we reach in the middle, then actually we can reduce too much the searching time and space. For example, if the solution is somewhere at depth d, then we can find the solution at x of the power d over 2. I mean, if x, for example, equal to 10 in our previous example, and we said that if the depth at d equal to 20, we needed 10 of the power 20 times that to reach to the solution in the breadth first. But here we reach the solution at 10 of the power 10. So 10 of the power 10 is actually much less than 10 of the power 20. And in this case, 10 of the power 10, if you multiply it with the computer speed is 10 of the power minus 6 microsecond required, 1 microsecond required for each iteration, then this problem could be solved at 10 of the power 4 second. It is 10,000 seconds. So 10,000 seconds, you can see that it is much less than 3 million years. 10,000 seconds can be, I think, maybe 3 hours or something like that. So the bidirectional strategy can be very efficient in case that you have the goal, and the goal is reversible. So we know the branches to reach to the goal. Okay. That said, the last thing that I just want to mention here, just to avoid repeated states, and I mentioned about this before, and I show it in the example of the puzzle 8. Me myself, many years ago, when I was writing some searching algorithms, it is really tricky. It is really tricky that you need all the time to keep big eye on the repeated states. Going back to the same state can be really like a hole in your code. Informed search, this we will keep it to the last clip in this topic 4, when we talk about informed searching techniques. Thank you very much and see you.